Hello everybody, I hope everyone's having a beautiful day. So today we're going to be talking again about binary trees. Now, I want to remind you of a couple pieces that we're going to need for discussing our next result that we're going to come up with together. So first, I drew a picture here of a binary tree. And as a reminder that we're specifically talking about rooted trees. So there's going to be a node that we designate as the root. So for example, there's the root. We typically will draw it at the top and then go downward level by how many edges or descendants we'll have away from the root. So we have a root so that we can dictate parent-child relations that these nodes can have. So for example, this node here is the left child of the root node, and this is the right child of the root node. So we draw them like this just for, and you find that there's many different drawings of this tree. We draw them typically like this because we like to have them in order of level. So level is another word for depth. So the depth of a node or its level is the number of ancestors that node has. So for example, the root node has no ancestors, hence it's at level 0 of the tree. How many nodes do we have on level 0, by the way? We have 1, right? We have 1 node. How about here? Well, we have 2 nodes in this particular tree. Now remember, this is a very specific binary tree. So I have 2 here. How about here? Well, we have 1, 2, 3, 4. There's 4 of them on level 2. And we have 1, 2, 3, 4, 5, 6, 7, 8. Well, it looks, it's just like double, it's like double the number this one has. And likewise, this seems to be the double of that, and so on. This one has 8. So if I went 1 level down, does anyone have a good guess on how many nodes you would find on this level if I gave every node exactly 2 children? How many would there be? Or how about how at most how many nodes will there be? Well, each of these 8 nodes here would have 2 children, so 16, right? Well, maybe there's a general pattern here that we sort of have an intuition for. It seems to be doubling at maximum. So notice I've maximized the number of nodes I have on each one of the levels. I'm not proving that here, but I'm just trying to explain to you that there seems to be a cap or maximum of how many nodes we can have on each level. One thing also as another piece of ingredient here, what's the height of this tree, by the way, this very specific binary tree? Remember, we're going to try proving a claim for any binary tree. What's the height of this tree? Well, what we do is we look at a node with maximal depth, aka nodes that are sitting on the level of the highest number, and we look at how many ancestors it has. So it's 1, 2, 3. Remember, I told you that the level dictates how many ancestors you have, right? Because the depth. But we can describe also that a tree has levels, and that's how we're organizing the nodes here. So remember, the number of levels, so just please keep that in reminder, is that the height of the tree is always equal to, of course, something interesting with the number of levels. There's something going on here. So if I were to ever ask what the height is, if I tell you how many levels there are, what can you tell me? Well, the height is always the number of levels less 1, or equivalently, someone can always tell you that, oh yeah, no, the number of levels is always the height plus 1. So just please keep this in mind when we look at this next claim. You might ask, Dan, why does that matter? Well, how do you know that? Well, remember, we start at level 0, and notice that the number here is the height. So 3 here is the height of this tree. Notice that I've counted number 0 here. That's another level, right? So it's 1 higher. So these are just this is just a little algebra here. Once I have one of the two, I can always get the other. But this is the one I want you to remember for our discussion here. Okay, so you can talk about what we're going to prove here in terms of the height or the number of levels. So I'm going to use the number of levels to talk about this next claim that we're going to prove together. So I'm going to refer to it as a lemma, because on its own it's interesting, but we can use it to prove other claims too. So here's the lemma. So for any binary tree T, with at least I plus one levels, the number of nodes at level I is at most 2 to the power of I. That's the claim we're going to prove. And we've already kind of seen how this works with an extreme example where we have lots of nodes. However, remember, this is just one binary tree. We have to prove this for any binary tree. So for example, it has to be true for this tree, this binary tree as well. If that's the root, for example. Likewise, it has to be true for that binary tree as well. Do note that, of course, this is true also for proper binary trees, hence why I've not said proper here. It's true for any binary tree. Specifically, we're talking about ones for which, if you ask the natural question of, okay, well, you'll notice that this is implicitly saying that it's non-empty. So just please keep that in mind, because it has to have at least some number of levels. We're not putting negatives into this thing. We're putting 0, 1, 2 as per the levels that we have here. This is implicit in the way this is described, okay? So just do take note of the way the statement works, as it says at least I plus 1 levels. So it's talking about the posit of an existing binary tree with at least some number of levels. So remember, the I plus 1 seems to have something to do with the number of levels of the tree versus the level itself being that one less, which should remind you of what we discussed around the height and the number of levels. So note that we can talk about a level versus the number of levels. Like if I look at level 1, notice that there's 2 levels here. It's one higher. This shouldn't surprise you because it's very much the same way that we're talking about things in terms of the height, for example. Which, remember, the height itself is a specific example of finding a node with a maximal depth. We might be just interested in a node with a particular depth, hence why we're looking at a particular level. Hopefully that's clear. So what we're going to do, so here's the game plan. We're going to prove this using mathematical induction. So this is the game plan. So I first got to say what we're going to prove. So we prove this claim using mathematical induction. Mathematical induction. Now, what should we use it on? Now we're considering weak induction, in a kind of classic sense. So we're going to have to use some variable. Now, what's a variable that's in this lemma that seems to be a natural one to use? Now, sometimes in induction proofs, it's not very clear exactly what variable you use every time. But here it seems to be rather nice. We might have a natural variable to use here. Well, we're interested in the number of nodes at a particular level we call I, right? And it's positing that we have a certain number of levels. Now remember, this part here is just saying that we have to have enough levels so that this level could exist. Is that clear to everybody? So for example, if I'm looking at, level 2, this is saying that that tree has to have at least 3 levels so that level 2 could exist. So notice this part is not actually that key at least at this stage. What matters is actually the level in relation to the nodes, so maybe we'll use induction on I. That seems to be, so we're going to be interested in that. For each integer, so we're going to come up with our statement. That says integer, by the way. It sort of got melted in the microwave like some cheese. For each integer I greater or equal to 0, which makes sense for the way that we're defining all of our terms here and how we're stating this lemma. This is the implicit part I was referring to. Okay, for each integer I greater or equal to 0, let S of I denote the statement. So this is what we're going to try to prove. The following statement. So we're going to call it S of I. So for a binary tree, and do note when I say a, I'm saying every for each, for all binary trees. I'm just talking about an arbitrary one. For a binary tree T with at least I plus 1 levels, there are at most 2 to the I nodes. This is I right there, by the way, on level I. So this is just me rephrasing this in terms of the variable I. Now, what do we do in a mathematical induction proof? So let me just remind you, just to give you just a little bit of a heads up of where we're going. So what we do is we start off with our initial base steps. And the way I like to talk about this is the same way. I heard this story years ago, but I'm going to adapt it for you for some fun. So I want you to imagine that Miss Kitty the cat wants to learn how to climb up a ladder to get into a bunk bed which has her bed in it. And Miss Kitty wants to go have a nap. Well, we can try to teach Miss Kitty in the following way. Well, we start off Miss Kitty, put her paws on the first rung and maybe some sufficient number of rungs so that we can maybe hopefully show and pick up Miss Kitty and put her on 2 arbitrary rungs to show her how she can get from one of the previous rungs to the next rung of the ladder so that Miss Kitty can climb up the ladder, up the rungs, into the bunk bed to go have a nap. And the way this works is very much like a set of dominoes where you set up your initial conditions or your initial what we call base steps. There may be one step, there may be multiple steps. Set up your initial steps, and very much like with Miss Kitty, what you do is you climb up, you put the initial ones in place, the initial base steps in place, and since you've shown how you can go from these initial steps to any arbitrary rung of the steps, you've actually taught Miss Kitty how to climb up the whole ladder to the top of the bunk bed. And that's what we're going to do here. So you might ask, Dan, is there like one solid way for determining a number of base steps? It depends on the claim. In fact, you can have as many base steps as you want. It's just more of the question of which ones are necessary. So let's just start off with thinking about the very first or smallest integer we're considering here. Let's consider the base step when I is equal to 0. So we're going to start with the very first rung. We got to put Miss Kitty's paw on that very first rung and see if she can go on that first rung. So this means that we're going to prove S of 0. That's what we need to do, is prove that. So what is this statement? So now let's look everywhere where we have 0. So I here is now 0. So S of 0 says for a binary tree T with at least 0 plus 1 levels, or 1 level, there are at most 2 to the power of 0 nodes on level 0. But what's 2 to the power of 0? It's just 1, right? So keep in mind, remember, we're proving this for arbitrary binary trees. So keep in mind that we're talking about any tree that has, oh, speaking of Miss Kitty, hey Miss Kitty. So right now we're trying to teach mathematical induction and have some fun for this particular claim, Miss Kitty. So what we're going to do here is we're going to look at any binary tree. So in this case, suppose there is an arbitrary binary tree with at least one level, But if there's at least one level, what does that imply? Because remember, we're talking about there being, remember, it's not going to look only like this node. This tree could look like this, for example. It could look like that. It could look like this, because it's talking about the at least. Notice it says at least at one level. But what can we say about that level? Since it exists, there has to be a node in that level. But what do we know that's very special about level 0? How many nodes can only have depth 1? Well, are we actually considering level 1? No, we're considering level 0, right? Remember, we're talking about level 0. So how many nodes are on level 0? Sorry, I'm getting you really excited. Because remember, that's level 1. Level 0 up here, what's this? Well, that's the root. The root is the only node that has no ancestors. So that's the only node that exists at that level in any binary tree. Yeah, so we're thinking about level 1. We're actually looking at this guy up here, just for clarification purposes. So what does that mean then? Implying, what is it? What's this implying then? There is at least one node. So what we're going to do is let's consider level 0. Consider level 0 of this tree. Consider level 0 of the tree. Okay. Here we have at most one node, right? But what is that node in this case? The root. This is just one node, but what's 2 to the power of 0? It's just 1. Hence, there is at most 1, which is equal to 2 to the power of 0. Remember, we're trying to establish this fact that there is at most 2 to the power of 0 nodes on level 0. Right? And S of 0 holds. So we proved S of 0. Is that clear to everybody? So we have a base step here. Now, let's think about this. Do we have enough information to get, are we convinced that this is true for arbitrary I? We've proven it for I is equal to 0, but do we need to consider maybe some more just to get ourselves convinced that this is actually true? Do we need more base steps though? That's another question. Now, if you're really not sure, think about this in a more arbitrary way. Okay? So suppose that we were looking at I is equal to 1. What would that mean? S of 1 would be for a binary tree T with at least 1 plus 1 level, so 2 levels. There are at most 2 to the 1 nodes at level 1. Now, this tree here shows that maximal property, but why can we say it's at most 2 in that case? Think about it. If there's at least 2 levels, we have these 2 levels. That means that there exists at least 1 node on each level here, but there may be more nodes later on in the tree by higher levels, right? So you might ask, okay, well, how many at most can be in here? Well, how did we figure it out for level 0 in our S of 0 case? Well, we looked and we saw, okay, there's at least 1 node, right? And we were able to imply that that was the root. That was what we did, right? Okay, well, how does a node get on level 1? How does it get there in this tree? How does it get to level 1 of the tree? Well, it has to be a child of a node on level 0, right? But here's the thing, in a binary tree, how many children at most are there for a node? So if I look at an internal node, like this one here in our particular example, how many children can you have at most? By definition, it's at most 2 because it's a binary tree. But notice it doesn't have to be the case. So your argument has to work regardless of that fact. For example, notice here, I only have a right child in level 1 of that tree. Here I have 2, but here I most certainly only have one right child. I don't have a left child in that case. So, but notice I'm getting an upper bound here, right? But I need to formulate this argument carefully so that I do not exclude cases like these. It has to be true for an arbitrary binary tree. But you notice when we walk through this idea, we're trying to come up with an idea of how we could approach this more arbitrarily. Notice that when I went one level down, I relied on information from the previous level. Maybe that's what we're actually going to need here for a more arbitrary run. Now, in my notes, I've included I is equal to 1, just so we could. So if you actually want to see how you reason out what we just verbally said here, you most certainly can. But let's proceed to the induction step. Now, the way I'm going to do this is I'm going to formulate this where I'm taking the previous statement. So I'm going to have S of k minus 1. I would like to prove that S of k follows from S of k minus 1. So now, technically speaking, in my notes, I also show how I is equal to 1, so S of 1 is true. But here I'm going to proceed from I is equal to 0. So what I do is I'm going to fix, we're going to fix some integer k greater or equal to 1. You might ask, why did I pick 1? Well, if I put 1 into here, I get 1 minus 1, 0. I've proven S of 0, correct? I would like to show that if I had S of 0, that it follows that S of 1 is true. That's what I would like to have. So I go find the largest value for which I've proven the base step. That's usually how I do this. That's where the 1 comes from. It's not just arbitrary here, okay? So let's proceed. So we're going to assume S of k minus 1. So I'm going to just say what that is. So for a binary tree T with at least, notice that, remember it was I plus 1, right? So now I'm going to do 1 less, so it's actually going to end up being k itself. Because it would be k minus 1 plus 1, which would be just k, with at least k levels. There are at most, now everywhere I had I, I'm going to put k minus 1. Remember? There are most 2 to the k minus 1, all in the exponent there is the k minus 1, nodes on level k. So I want to assume that this particular statement holds. That's our induction or inductive hypothesis. I label it as IH. So what we want to do is we want to show, as I'm going to say in a moment, that S of k, it follows from S of k minus 1. So let's just say that. Now for the sake of brevity here, I'm going to not write what S of k is, but I would, in my notes, and this is what I typically would advise you to do, is write what S of k actually is. This is just for the sake of brevity here. We show that S of k follows from S of k minus 1. So just as a reminder, everywhere where I had I put a k. So we actually wrote it out over here, except everywhere it was I. Now I'm going to replace that with k. So what do we usually start at? Well, we say what we're going to go about with, right? So what we need to do is we need to consider an arbitrary binary tree T T that has at least, now remember, for S of k, it would be k plus 1 here, at least k plus 1, just like we had I plus 1 over there. At least k plus 1 levels. So what can we say about if there's at least k plus 1 levels? Well, let's look back at our picture here of this particular tree, but what really matters is the levels, okay? So observe that T then has at least k levels. Implying, so I'm not actually looking at level k, I'm actually looking 1 up. You know, kind of like our idea we had over there. Implying this is level, by the way, level k minus 1 exists in T. But what can we say about level k minus 1? Well, look up here. If there's at least k levels, do you see something that we did wrong up here? Nobody caught this one. I should say k minus 1 there. So that's really interesting, right? So we have level k minus 1 actually. So notice that actually right there really matters. So this is why you have to be very careful when you write out what the statement is. So take a look here. So now we got a statement here. So if it has at least k levels, which ours most certainly does, what can you say about that number of nodes on level k minus 1 then? Well, the IH here, our induction hypothesis, says that there's at most 2 to the k minus 1 nodes, right? So let's see here. Well, since we can just straight up use the induction hypothesis on those upper levels, right? In fact, we can use the one just above it. So by the induction hypothesis, level k minus 1 has at most 2 to the power of k minus 1 nodes. But let's go back to what we were thinking about when we were trying to think about proving S of 1. Why did we say that there was at most 2 here? How did we know that fact? It's because it's a binary tree, right? We have at most how many children? At most 2. Since t is binary, at most 2 children exist on level k. Right? But it's not, we have to be a bit more precise about this, right? Not just on level k, but where do they come from? For each node on level k minus 1. So that's its level, by the way. So let's go back to what we had over here, if we actually think about that then. Since t is binary, if I were interested in level 1, well, I look at the one at level 0, right? Just like I'm doing here, I go up 1 level, i.e. my level count, my level number goes down 1 by going up. Well, notice here, well, this is the node that's at level 0. It has at most 2, hence why I'm doing this. But where do they come from? These are children of nodes on level 0. Just like when I talk about an arbitrary 2 levels, I could say that. So now that we have this here, let's actually now put it all together. Thus, it follows that the number of nodes on level k is at most 2 times 2 to the k minus 1. Remember, this is, we got this from the previous level. The level is directly above, which is equal to 2 to the k, which that's what we want to establish, right? That's what S of k wants us to have here, right? Completing the induction step. So now we've done the induction step, that is finished. Now we have to do the last piece, where we need one more piece to complete the proof, to use mathematical induction correctly. Well, we actually have to invoke the principle of mathematical induction. Therefore, by the principle of mathematical induction, or PMI, for any binary tree T with at least I plus 1 levels, the number of nodes at level I is at most 2 to the power of I, and that completes the proof.